So today I'm going to talk about Green's conjecture. And let me recall from yesterday's lectures the following. If X was a complex projective variety, and L was a line bundle on X, we have defined the Koszul cohomology space of X with values in this line bundle L as being the cohomology at the middle of the complex. And here we had wedge P plus 1, H0 of L, tensor H0 L Q minus 1, wedge P H0 L, H0 LQ, and wedge P minus 1 H0 L, tensor H0 LQ plus 1. And we have seen that this all these Koszul cohomology spaces know about the minimal resolution of the module direct sum H naught of all the powers of L. And we have seen that also that Lazarsfeld found a very nice relation with geometry using kernel bundles. And I hope to convince you during my talk that there is way more geometry behind these Koszul cohomology groups or spaces than just computing minimal resolution, which is a purely algebraic thing too. And the first one, the starting point was the non-vanishing theorem of Green and Lazarsfeld. Which basically said the following thing. If X was smooth and L was decomposed as a tensor product, L1 tensor L2, such that every Li has at least two independent sections, then they are able to construct non-zero Koszul cohomology classes in this space. And so basically we are going to look at spaces of type KP1, just KP1s. So that's the first non-trivial, so in the Betti table, that's the first non-trivial row. So this is the row of KP1s. And the first basic observation is the following, that if we have a vanishing at some point, so if KP1 XL is 0 for some P, then we will, for some P at least 1, then all the others will be 0 for any P prime greater than or equal to P. If we think of about minimal resolutions, this is almost automatic, because if at some point here we have a 0, then what follows will be just remember that on the linear strands we read linear relations, on the diagonal we read quadratic relations, and so on. So if we have those 0 here, what's next will also have to be 0 because there will be no relations. There's no way that we can produce something non-zero here as relations. Okay, so that's there are several proofs for this property. This is no longer true for KP2s, for example, or other KPQs. So that's something specific for KP1s. And likewise, this theorem of Green-Lazarsfeld produces non-zero Koszul cohomology classes here in this space. But for the moment, we have no such general method for constructing classes in other KPQs. So that's the only general case I know so far that where we are able to produce classes out of some specific information like this. Okay. So let's see now what happens. So Green's conjecture is a statement that predicts optimality of this non-vanishing result in the specific case of canonical curves. So let's see what happens if we apply Green-Lazarsfeld's result for a canonical curve. So let's assume X is a smooth curve, and L is the canonical bundle of X. And if we want to apply this theorem, we need to find a decomposition. So we just decompose the canonical bundle as A direct sum B. Of course, B is K of minus A. And we need to have both H0 of A and H1 of A, at least 2. Right? In order to be able to apply this statement. And the quantity appearing here, this integer, I'm going to compute it in a moment by using Riemann-Roch. So first of all, just take the following natural map. That's just the addition of divisors. This is the sum of divisors. Of course, just by definition, that's finite on the image, because given any effective divisor here, we can only find finitely many ways of decomposing this divisor. And the codimension of the image is, by definition, what's called the Clifford index of the bundle A. And by Clifford's theorem, that's oh no, sorry, that's it's just a codimension, so it's automatically bigger than or equal to 0. Let's find now the relation between this quantity and the Clifford index. So the Clifford index will be, of course, genus minus 1 minus H0A plus 1 minus H1 of A plus 1. And now we apply Riemann-Roch for, let's see, this here. And by Riemann-Roch, this is minus the degree of A minus H0 of A. So that's simply the degree of A minus twice H0 of A plus 1. And applying again Riemann-Roch, we see that that quantity, R1 plus R2 minus 1, in this case is just G minus cliff of A minus 2. So in other words, what we have obtained here is I'm sorry, that's yeah, it's just the definition. That's well, that's another interpretation of the Clifford index, but this is just
2 H0
plus 2. Yes, thank you very much. Yes, plus 2. So that's not Riemann-Roch. That's just the definition. By definition, we have this quantity, this equality. So in other words, Green-Lazarus non-vanishing theorem yields here Kg minus cliff of A minus 2, 1, x, kx is different from 0. So this is what this result gives us here, in this case. And of course, this applies for any A with these two conditions, right? So the only conditions required are these two in order to be able to apply the theorem. So in particular, we can also we obtain the same result for an A which whose Clifford index is minimal. So in particular, if we define the Clifford index of the curve as being the minimal of all the Clifford indices of all bundles with these two conditions, then we will have K G minus cliff x minus 2, 1, x, kx is non-zero. Okay, so that's what we got. So out of this statement, we obtained one invariant. That's an invariant of the curve. So cliff is an invariant, a numerical invariant of the curves, and we have the following property. Cliff is lower semi-continuous, and is bounded by the integer part of g minus 1 over 2. So we only have finitely many possible Clifford indices, and this provides us with a stratification of the moduli space of curves. So this gives a stratification of the moduli space of curves of given genus G. So the open stratum corresponds to the maximal value. So the set of points corresponding to curves with maximal Clifford index inside MG is open, a non-empty Zariski open set. And the minimal value, for example, which is 0, is obtained for hyperelliptic curves. It's actually if and only if C is X is hyperelliptic, meaning that we have a 2-to-1 cover to P1, and this 2-to-1 cover is actually obtained from a projection of the canonical system. The canonical system has the image, the P1 embedded in a PG-1. And this Clifford index, which we found so far, is related to another invariant, which is the gonality, in the following way. So recall that the gonality of a curve is by definition the minimum degree of finite cover to the projective line. X. I tend to write C for curve. That's why. So C, every time I write C, is actually X. So that's the two are related in the following way. So we have one equality which is just the definition. The Clifford is bounded by gonality -2. So that's just the definition. And the other inequality is it's greater than or equal to gonality -3. And that's a theorem by Coppens and Martens. So they are really very, very close to each other. And conjecturally, well, the exact relation between them is still not very well understood, but conjecturally they should be related in the following way. So this conjecture was made by Eisenbad, Martens, Lange, and Schreier. So cliff of a curve is P if and only if either the gonality is P plus 2, or the other possibility would be that X is a plane curve of degree P plus 4, or P is odd, X is in P plus 3 over 2 is a half canonical curve of genus 2P plus 4. So these are somehow the possibilities, and in that case, half canonical means that the square of the hyperplane section is just a canonical bundle, and the hyperplane section computes the Clifford index in this case. So this should be. There is a lot of evidence for this conjecture, but still, it's still open. So, well, however, coming back to our discussion on the Koszul cohomology of the canonical curve. So we obtained here this non-vanishing result. So Green's conjecture predicts that this is optimal. So more precisely, Kp1 of x, Kx should be 0 for all p at least g minus cliff of x minus 1. Which by the remark we made at the beginning can be reduced to checking the vanishing for p equals g minus cliff minus 1. And remember from yesterday that we had duality. So the Betti table of the canonical curve was symmetric with respect to the center. So that was the Betti table of the canonical curve, ending at the G minus second column. And so here we had some non-zero entries, starting at 0. So just by applying duality, this says is exactly the same as saying that Kp2 of x, Kx is 0 for any p lower than or equal, strictly lower than Clifford index of x. So this says precisely that the number of zeros here on the second row, well, that's the 0th row, that's the first row, the second row. The number of zeros should be equal to the Clifford index of the curve. And that's what it says. And in terms of minimal resolution, that's also interesting to see. It says the following, that so on the first column, we just read the degrees of the generators of the ideal. So it says that the ideal is generated by quadrics. Well, first of all, how about the 0 here? So this is non-zero if and only if the curve is non-hyperelliptic. And if the curve is not hyperelliptic, we knew that's the theorem of Max Noether that the image is projectively normal, the image of the canonical curve. Then for the next statement, it says that here, if we have a 0, then the ideal is generated by quadrics, unless the Clifford index is 1, which can only happen if we have a 3-to-1 cover of P1 or we have a plane quintic. And this is also a classical theorem of Enriquez and Petri. So if this conjecture was true, it would say that the ideal is generated by quadrics and the relations are linear up to the step given by the Clifford index and the minimal resolution. It's basically a purity condition of the minimal resolution of the canonical curve. So that's the meaning of Green's conjecture in terms of of minimal resolutions. And I'll talk more about it on my talk, on my conference talk on Thursday. For today, I would just like to discuss the main result in this direction. So the major breakthrough in this direction was realized by Claire Vazin in two papers, in 2002 and 2005. Well, she proved that the conjecture is true for a general curve. So Green's conjecture is true for a general curve. And I will just give the main ideas of the proof without going into the details. So let me just say at the beginning that there are many innovative approaches in the proof. So if you just have a look on the papers, you will see that there are many nice problems which are solved step by step in order to achieve the result. Okay, so the first idea is, so the first step would be to apply semi-continuity. So by semi-continuity, if we want to prove that something, so remember that Green's conjecture is a vanishing statement for a Koszul cohomology. And by semi-continuity, if we want to prove vanishing for some set, it suffices to prove vanishing for one given point. So by semi-continuity, it suffices to find one general curve, whatever general means, satisfying Green's conjecture. And what's the meaning of the general here? So it's general in the sense of the Clifford index. So for a general curve x in Mg, the Clifford index is precisely g minus 1 over 2, integer part. So it would be enough to exhibit one example of a curve of maximal allowed Clifford index for which the vanishing predicted by Green's conjecture is true. Okay, and these examples are curves on particular K3 surfaces. And these K3 surfaces are the following. I'm just going to give. There are two cases. So the first is for even genus. G is to K. So that was the first paper. So for this case, S is a very general K3 surface. So the Picard number is generated by the Picard number is 1, and X was a curve in is a curve in the linear system L. Of course, we need L squared to be 2G minus 2, so L squared must be 4K minus 2. Okay, and we wish to prove here, so if we just compute G minus 1 over 2 integer part, we realize that we need to prove that K1 x Kx equals 0. So that was the even genus case. And for odd genus case, her choice was a bit different. This is for technical reasons. So G is 2K plus 1. This time S is not very general, but has Picard number 2. So the Picard number is generated by a very ample L, and so L is very ample with L squared equals 4K, and delta is a smooth rational curve, and L intersects delta into, so the intersection number is 2, and again X is a curve in L, and we need to prove once again that Kk1 of X Kx is 0. So you see that these are some choices of K3 surfaces. Of course, you may ask why K3 surfaces. Why not other surfaces, like abelian surfaces or whatsoever? So why K3s? So there are several reasons for that. So the first reason is that for K3s, we have the hyperplane section theorem. So by the hyperplane section theorem, and this says that the Koszul cohomology of the surface and of the curve are the same. So Kp1 of x Kx is the same, and this isomorphism is just given by restriction to Kp1 of S and L. So in both cases, we have to prove that K1 of S and L equals 0. So we are reduced to proving some vanishing. So we are reduced to a vanishing statement for a surface. And what's the advantage of that is that on the surface we have plenty of geometrical information which we can use. On S we have plenty of geometrical objects. Whereas if you just take one random curve of maximal Clifford index, there is very little. There are very little things to use in order to prove the desired statement. So in particular, the Brill-Noether theory of the curve x. What I mean by Brillanter theory is just the study of special linear systems on the curve is governed by rank 2 vector bundles on the surface S. So we can apply the powerful machinery of vector bundles, of the theory of vector bundles, on the K3 surfaces in order to relate them to linear systems on the curve. So this is one kind of one type of piece of information that Claire-Vazin uses to prove this thing. And there is another ingredient which was completely new, completely unexpected, and very innovative, I would say, which was a new interpretation of Koszul cohomology in terms of Hilbert scheme. So that's probably the critical point of every proof. Any major proof has some critical point, and if you reach this critical point, then you say, okay, maybe the proof will go through. Probably this interpretation is a critical point, but anyhow, the proof itself is very, very technical, so and it's very long. So one needs plenty of other things to do beyond this new interpretation. Okay. So let me just discuss very briefly what this new interpretation of Koszul cohomology in terms of Hilbert schemes. So that's a very general setup. So X is just the smooth, complex projective variety. So not necessarily curve or K3 surfaces or whatsoever. L, a line bundle on X, right? And we wish to have to express these Koszul cohomology spaces in terms of Hilbert schemes of X. And let me denote by X n. So this is the Hilbert. That's the Hilbert scheme of zero-dimensional subschemes of length n on X. And X n C, little c, inside here. C stands for curvilinear, so this is inside Xn. So these are curvilinear subschemes. Curvilinear means that in some analytic coordinates we can express such a scheme as being given by equations like Z1 equals Zn minus m minus 1 equals Zm to some power p equals 0, where Z1, Zm are local coordinates on the variety X, and p is lower than or equal to our n. Could be n if it's supported in a point. Yeah, that's the definition of curvilinear. Yes.
What is M? M is the relation.
M is the dimension of X. Yeah. I mean, you have.
M is dimension of the X.
Yes, yes. I mean, I should have taken N for the dimension of X, and yeah, but I don't want to change the notation. So these are really subschemes that lie on smooth curves on the variety, that are locally supported on smooth curves on our variety. Okay, and this is so X and C is a large open subset in a connected component. Actually, that's directly in Xn. Large meaning that the codimension of the complement is at least two-dimensional, and this is connected. If our variety was connected, because simply any curvilinear subscheme is a limit of a reduced subscheme. So this contains the connected open subset of the Hilbert scheme of reduced subschemes. And now we can take the product, and inside the product we have the incidence variety, Cn. So this is just Cx, such that x is in the support of C, and we have two projections. Let me not mix them up. So P is on X and Q is on X and C, little c. And Q, of course, is finite, of degree n. And now we had our line bundle here. What we do is just the usual thing: pull it back, push it forward. So we define Ln to be Q lower star, P upper star of L. That's just a rank and vector bundle on X and C. So basically what we do is if we have C in X and C, so we can see it in two ways, either as a point here in the Hilbert scheme, or a collection of, or a subscheme of X. And now we take L restricted to C. That will be a vector space of dimension n. And if we see C as a point here, then this will be the fiber of the new vector bundle. So that's just the fiber of Ln over the point C. Okay. Now we have an evaluation map. Which goes from H0 L tensor O X and C to Ln. And just by taking wedge products, wedge n, take wedge n and global sections, and you get the following theorem, which was proved in the same time by Vazin and Ellingsrud, Götze, and Lehn, which says that wedge n, the induced map to H naught x n c that Ln is an isomorphism. And now it's pretty clear what's the game we play here. So we try to replace every time we meet some wedge somewhere, we try to replace it by this space of sections. And Vazin manages to do that. And she proves the following. That KP1, well, it's also true for any KPQ, but let me stick to KP1 because that's simpler, is isomorphic to the co-kernel of the map from H naught x p plus 1 c that L p plus 1 to H naught of c p plus 1, and here we have q upper star, so this is q upper star map, q upper star of that L p plus 1. If you wish, this is the same as H naught x p plus 1 c times x, and now we have the projection upper star of that L p plus 1, and this is the just the restriction map. So the difficulty now, the problem of making some Koszul cohomology group vanish becomes a problem. This is that's a restriction map. That's a sub variety here inside this product. And now all you have to prove is that some restriction map, these are line bundles, some restriction map is surjective. And that's what she does for the rest of the proof. So for S as before, so S one of the two K3 surfaces, she manages to prove in a very, very smart way that this map is actually surjective. So she uses plenty of techniques like base change and so on, vanishing results. So I think I'm going to stop here for the moment.